Hey guys, we're about to get cranked up into two-dimensional motion, but before we do that, we have to learn vectors in a little bit more detail. That way we can actually deal with this 2D motion idea. Now, remember, a vector is simply a measurement with a direction, right? Any number with a direction. And so we can use arrows to display that. Sometimes they're nice and easy, one-dimensional like this, right? I have, let's say this is 5 meters per second, plus another 5 meters per second going the exact same way gives me an outcome of 10 meters per second. Or if they're going opposite ways, positive 5, negative 5, notice the opposite directions of the arrows leaves me 0 meters per second. So adding them up or subtracting them whenever they're going the same way, right, or opposite ways like in this one, or same way like in this one, is relatively simple. But what about whenever we actually are moving in 2 dimensions? We're not getting into 3 dimensions this year in this class, just 2 dimensions. So in other words, left, right, backwards, forwards, not the up and down part, or we can rotate that axis and go up and down a little left and right or backwards and forwards. We just can't combine all 3 just yet. So anyway, what happens whenever they're going in different directions? How do we add those up and come out with a resultant vector? The answer whenever you add vectors is always called the resultant. So whenever I have 2 vectors, let's say the person is running along vector A, so with 10 meters per second like this, but the wind is incredibly strong, it's blowing them like this, vector B. What actual path will the person take? What is the resultant path? C. All right, so just simply working on drawing vectors. Look at number 1 now. I've got 2 vectors here that are going the exact same direction. Okay, so 2 vectors going the exact same direction will give me a resultant that is the exact same length. That's my resultant R, or the answer whenever those 2 vectors are added up. On the other hand, number 2 has 2 vectors going the opposite way. That means I am subtracting them. Notice this is done without numbers. This is just all pictorially. Whenever I am subtracting vectors, well, let's actually grab the correct one here. I actually can drag vectors around. I do want to point that out. Vectors can go anywhere you want them to go as long as they maintain the same magnitude. That means the same length or the same number measurement, 10 meters per second, 5 meters per second. So as long as they maintain the same magnitude and the same direction, that which way they're pointing, they are the exact same vector. So I can take this vector and, if you will, stack it. Something like that, right, to where it's very easy to see the resultant runs from the tail to the other tip, R, right? So from the first tail, it went all the way over here and then all the way back. So the resultant R looks like this going to the right. Now those are 1 and 2 are relatively simple. 3 becomes a little bit different. Notice these 2 vectors are not going the same direction or opposite directions. Instead, they are at some angle to each other. They are also what is called tail to tail. Anytime you have tail to tail vectors, you are going to create a parallelogram similar to this. Think of copying and pasting. So I'm about to take this vector here. Notice I indicated which one it was, and I'm about to paste it to the tip of the other. So I'm going to copy, paste, to where it's identical. In other words, the one directly across, paste it directly across from it, and then I'm going to do the same thing with the other, right? So this should have the same magnitude and direction. Here I'm freehanding it just to get the idea very quickly. But it's best to use a ruler and protractor. Then the resultant runs from the tails to the tips, which should be logical to you. If you think about it, someone, let's say this is a force vector diagram, and so I have, let's say, a tree stump that we're pulling on with a couple of tractors, I don't know, and one tractor pulls like this, and another tractor pulls up like that. Well, which way is this tree stump going to actually get pulled? Well, the answer is in between them, from where the stump actually is, coming this way. Some people have a bad habit of drawing the resultant vector over here like this, and that makes absolutely no sense because that's not where the forces were getting pulled from. You got to look at the base, where they were actually getting pulled from. 3. So here's another little practice in 4. And there you go, there's your resultant. Some people get very freaked out whenever the angle is above 90 degrees. Don't be, it's not a big deal. I simply take this guy and copy, paste him up on top of the other guy. Notice now, they were tail to tail, and I copy paste him on top where it's tail to tip. So here's a tip, there's a tail, right? These two were tail to tail. So I copy, paste, and then I'm going to take him, copy, and paste, same direction, same magnitude. You can see I didn't get this lined up perfectly. Notice the two blue arrows aren't perfectly aligned there in the end, and the resultant runs from the tails to the tips. Now this is even easier whenever they're already set up in a tail-to-tip fashion. In tail-to-tip fashion, you don't actually have to create a parallelogram like you do over here. Tail-to-tail is parallelogram, tail-to-tail, parallelogram, copy, paste, resultant, right? But whenever they're actually tail-to-tip from the very beginning, all you have to do is complete the triangle. That's simple. And it runs from the tails to the tip, from the first tail to the second tip. And there's your resultant. If you have two or more vectors, you add them just like you do in math. So in math, remember, if we were adding 2 plus 3 plus 5, you just simply pick two of the three numbers and add them to start out with. For example, you might add 2 plus 3 and you end up with 5 plus 5. And 5 plus 5, then you add, after you've added two of your numbers, right, these two numbers to get their resultant, you add their resultant with the leftover number, so now 5 plus 5 equals 10. You do the exact same thing with vectors. I'm going to pick two of the vectors and add them to start out with. Now I'm going to start out with the top two vectors. Notice they are tail to tail, so I'm going to use the parallelogram method. All right, so I have added those top two vectors. Notice this vector plus that vector gives me this resultant, because copy, paste, let's actually put in a couple of lines up there showing they are the same, and then copy this one, paste it here, and the resultant runs from the tails to the tips. Now, I have the resultant of those first two vectors, and just like in math, whenever you add two numbers, right, if I add 2 plus 3, I get 5, and the 2 and the 3 no longer exist. Instead, only the resultant exists. That's the exact same way in vectors. It's just that it's not exactly easy to go back in and erase all of this stuff here, but all of this stuff is found in the resultant. So don't even worry about the other two vectors now. It's all found in the resultant. I am going to now add the resultant of these two, right? This is 2 plus 3 equals 5. I'm going to add the resultant of those two with the one that was left over. This guy down here. Now they are tail to tail also, so I need to use the parallelogram method. And in green, I get my final resultant. I put R total or RT final, R total final, or our final answer there in green. Don't ever get freaked out whenever you have more than one vector. You simply just add two of them, get their resultant, then you add their resultant to whoever's left over, imagining that the other vectors weren't even there, imagining all that's there is the resultant and the guy that was left over to get the final vector. One last note, this can also all be done to scale. So notice now I have two vectors with their magnitudes actually listed, 12 meters per second, 8 meters per second, and I want to get a resultant. Now the resultant is actually very easy to draw, right? This is a tail to tip guy, right? So notice the tail to tip intersection. So all I have to do is complete the triangle. R runs from the tail of the first to the tip of the second, completing the triangle there. But the question is, what magnitude does that get? The way you figure that out is you use a ruler. So whenever I drag a ruler up here, I see that this vector is approximately 6 centimeters long. 6 centimeters. And whenever I drag it down here, let's rotate. Whenever I drag it down here, I see this vector is approximately 4 centimeters long. So 4 centimeters. That tells me that for every centimeter, 1 centimeter on this pictorial vector must equal 2 meters per second, aka divide, right? Every centimeter equals 1 meter per second. Well, now I have my scale, so I can move my ruler back up here and measure that distance. That looks like 7 centimeters to me. So 7 centimeters, meaning that this entire red vector is going to represent 14 meters per second. That's how you do them to scale. You measure, you're told what each thing is worth, so you measure them, right? to figure out what the scale will be. So you write down how many centimeters, how many millimeters, or whatever it is. That will allow you by division to figure out what the scale is. 8 meters per second is 4 centimeters. Thus, 1 centimeter must equal 2 meters per second. And you see that lines up over here. Also, measure your resultant with a standard measurement, 7 meters per second. That then allows you to then use this combined with your scale to figure out what the answer would be.